So welcome to this video on ratio and proportion, and we're going to look at two kind of big ideas. First up, the first one is that areas of triangles which share a height are in the same ratio as their bases. Let's just take a look at this. Okay, so here we've got two triangles. We've got a red one and a green one, and in fact we've got three triangles because there's actually the big triangle that comprises both of them. But what do the red triangle and the green triangle share? Some people might say, well, they share a kind of a side going along there. That's true, but it's not relevant, all right? What's relevant is that they actually share a height. Now, it's not obvious that they share a height, but if we turn the diagram around, and you have this ability when you're doing an exam, if you turn the diagram around, I think you can see now that the two triangles share a height. And I'm going to put that height in. There it is over there. Okay, so now let's take a look at the ratio of their areas. So if we look at the red one's area, it'll be half the base of 2.48 times this height. The green one's area will be half the base of 7.31 times the height. And if we look at this calculation over here, the halves divide out, the heights divide out, and we actually get just the ratio of the bases. Right. And we can see that if I go and change this, the positions here of the green and the red triangles, the sizes of the bases, the areas change, but the ratio of the areas are fixed in the ratio of their bases. Okay, so just remember, it doesn't matter how the diagram looks, even those two triangles actually share a height. If we had to draw the height in, there it is there. Okay, really, really important idea, and one that a lot of people struggle to pick. The second big idea is that the areas of similar shapes are in a ratio which is equal to the square of the ratio of their sides. Let's take a look at this one. Okay, so what we've got over here, we've got two rectangles. These two rectangles are similar. The ratio of the sides is 1:2, right? In other words, this here is half this here, all right? Or this here is double this here. But in fact, the areas are in the ratio 1:4. And the reason for that is that this length over here would actually fit in once there and another time there. So this blue shape would fit in twice in the width, but also twice in the height, which is why it's 4 times bigger. If we just show the sort of construction lines, I like to think of this as almost like a projector globe, this being the blue rectangle, and the gray rectangle is actually the shadow on the wall. Okay, right. If we change the scale factor to 3, you'll notice that the area actually goes out to 9 times as big. Okay, the rectangle's actually fallen off there. If I change the center of enlargement, we can see kind of what's happening there. So if the sides are in the ratio 1:3, the areas will be in the ratio 1/3 squared. Now, all of this is easy to see with rectangles, but in fact it's true for any shape. Right, so if I go and change this shape, all right, any two similar shapes, all right, including a triangle, whatever shape it is, if the sides are in the ratio kind of A:b, the areas will be in the ratio A²:b². Really, really important result. Then before we dive into solving a question or two, there's an important strategy, and that is that when we put information about ratios on a diagram, we should use variables. So for example, if we know that AB to BC is 2:5, then don't write 2 and 5 on the diagram. Rather write 2m and 5m, because we don't know the actual lengths, we know the relationships between the lengths. Okay, let's dive in and look at a couple of questions. Right, this first one over here, what we're told is that BD is 6 centimeters. That's an actual length. And DC is 9 centimeters, that whole line from D to C. We're then told that AT to TC is 2:1. Now, I'm not going to write a 2 and a 1 here. Otherwise, I might think that this is 2 centimeters and this is 1 centimeters. I'm going to put variables on those. So I'm going to say that this is, so for example, I'm actually not going to use M. I'm going to use P. The reason I'm not using M, it might be confused with meters. 2P and 1P. I don't know the lengths of these lines, but I do know the ratio that they are in. Right, next up, the question asks me to just write down the value of the ratio CE to ED. Okay, and again, this is where it's helpful to maybe turn your sort of book around. But what we're seeing here is we're seeing these parallel lines. All right, we want them quite that thick, but there they are. All right, and because of those parallel lines, we have got our proportional intercept theorem. So CE as to ED is actually going to be exactly the same size as CT as to TA. Now CT as to TA is actually 1P as to 2P. The P's can divide out and we get a half. The reason, right, and they didn't ask for a reason, but it's always good practice to give a reason, is proportional intercept theorem or line parallel to one side. Show that D is the midpoint of BE. Right. What we now know is we know that CE to ED is 1 as to 2. So let's put that information onto this diagram using a variable. Okay, so I'm going to say that this is, say, 1K and this is 2K. Now we can see that in fact 3K is actually equal to 9 centimeters. All right, so therefore K is actually 3 centimeters. So therefore DE is 6 centimeters. And if DE is 6 centimeters and BD is also 6 centimeters, then D is the midpoint. Of BE. Next up, it says if FD is equal to 2. Right, now FD is this line over here. Right, we know that this is 6, and we know that this is 6. These are actual lengths. All of these are actual lengths. Right? Now the question is asking, what's the length of TE? And the kind of secret to this one comes from realizing that this triangle this yellow triangle over here, right, is actually similar to this green triangle over here. Okay, we can see why it's similar. It has a common angle and it has corresponding angles on parallel lines. So the little yellow triangle and the green triangle are similar. Right, so let's just write them down in terms of the order in which they're similar. Triangle BDF is similar to triangle BET. And the reason for that is angle, 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 3 angles. Now because of that, we can pull out some ratios. Right, I'm interested in the length of TE. So if I take TE out of this back triangle, the second triangle, I must take DF out. Now I want to take another length out of this one, hopefully one which I know, and I do in fact know BE. So if I take BE, then I must take BD. Now the reason I can do this is because I've got similar triangles. Okay, let's put in the variables that we know. We know that DF is 2. That's what we've just been told in this question. We know that BE is actually 12. And we know that BD is 6. Right. A little kind of quick trick with ratios. If you've got two fractions that are equal, then a quick sort of way of simplifying them is that the top of the one multiplied by the bottom of the other will be equal to the top of the other one multiplied by the bottom of the first one. So in other words, 12 times 2, 24. So finally, TE is actually 4 centimeters. Still on the same question, we now are asked to calculate the ratio of the area of ADC, that's this triangle on the right hand side, and ABD, the one on the left hand side. Remember that this was 6 centimeters. This was 6 centimeters, and this, the ratio of DE to EC was 2:1, so in fact this is 3 centimeters. Now here is where one of our big ideas comes in, because this triangle over here and this triangle over here, the green one and the red one, what do they share? Well, they share a height. That height would drop down somewhere there. Because they share a height, their areas will be in the same ratio as their bases. In fact, we've got the red one over the green one. So the red one's base is 9, the green one's base is 6. That can obviously simplify to 3/2. The reason for this is shared height. The next one says calculate the ratio of this little triangle here to the whole triangle. Okay, now this is slightly more interesting, right? Because in fact this triangle is actually similar to this triangle, right? And if we look at it, remember this was kind of 1K and this was 2K. So I'm talking about the blue stripy triangle and this red triangle. They are similar. Their sides, right, are in the ratio 1:3. This is the other big idea. Their areas will be in the ratio 1 squared as to 3 squared, or 1:9. In other words, the red one is actually 9 times bigger than this one. So what I'm going to do now, in exactly the same way as I can put lengths of lines on using a variable, I'm going to say, hang on, I'm going to let this little area here be 1A. The whole red triangle is 9A, which means that this kind of zone over here, let's just put, I'm actually going to just color it with sort of little blue dots. That's going to be 8A, because the whole thing is 9A. So the blue dotty piece is 8A, the whole red triangle is 9A. Right, now what we are interested in is what proportion is TEC, the little blue stripy triangle, out of the whole triangle. But remember what we've done up top here. We've looked at the ratio of this as to this, and we discovered that in fact the red one to the blue one is 3:2. So the red one's actually 1.5 times the size of this one, right? So if this is 9A, this in fact must be 6A, this piece over here. So in fact the entire big triangle ABC is actually 15A, and the ratio TEC as to ABC will be 1A as to 15A, which is 1/15. Okay, hope you found this video useful. If you did, please like, share, and subscribe. Thank you.